Okay, today we have a shorter spectroscopy lecture. You don't have to turn in your stuff right now, but turn it in before lab. If you're sitting there like completing it, I think I'll notice. Maybe. So what we're going to talk about today, and it's not as long because there's only a single page of notes, is the idea of ultraviolet and visible spectroscopy. Now, if you've done any kind of colorimetry or spectroscopy in like analytical or general chem lab, where you've measured absorbance of a colored solution, you've used UV visible spectroscopy. But in this case, we're going to talk a little bit about where the color comes from, what ground state and excited state we have to get us an absorption of visible or ultraviolet light to make something a color. And in organic molecules, what we're looking for is double bonds that are in conjugation. Later on in lecture, you'll find out that conjugation means that you have a double bond, a single bond, and a double bond. So the double bonds are alternating, and they're separated by a single sigma bond, or a single bond. And what will happen is it turns out that the longer that conjugation, the more double bonds you have in conjugation, the longer the wavelength of light it absorbs until it moves from the ultraviolet to the visible. And once things absorb visible light, they have a color to them. They're not colorless anymore. Okay, so we'll talk a little bit about where this comes from. And it requires looking at bonding from a slightly different angle. Okay, we've talked about forming covalent bonds by sharing electrons, by overlapping orbitals head-to-head to form sigma bonds and sideways to form pi bonds. Well, the real mathematics in forming a single bond is to look at what's called the wave function psi. And psi is the mathematical description of how the molecule, or how the electron moves around the nucleus as a wave. Okay? And that wave function can either have a positive sign or a negative sign. In other words, it can either have a positive amplitude or it can have a negative amplitude. So when you take two hydrogen atoms and you bring them together to form a hydrogen-hydrogen covalent bond, what you're doing is you're overlapping two waves to get what we would call construction, I guess, in physics. You'd have constructive addition of the waves. So in other words, what would happen is you would have something that looks like this from just a purely sort of physics standpoint. If you took said, well, okay, here's my x-axis, xy-axis of the wave. And I had just some sort of sine wave or cosine wave. There's two possibilities if I bring two waves together. If the two waves, like in this part, let's say, when the two waves have the same sign in terms of amplitude, what happens to them? They reinforce each other, and the resulting wave that you get from the addition is bigger. And that's going to be sort of reinforcement of the waves. On the other hand, and this wouldn't happen with one single wave, but if you had a negative amplitude with one wave and a positive amplitude with the other, then they would basically interfere with each other. They would destruct, and the resulting sum would be no wave. Right? I mean, basically, that's how you kind of look at waves in physics when you bring them together. It's just the addition. Well, in an orbital, or the description of the electron, the wave function can either have positive or negative amplitude. So if we bring two wave functions together that both have a positive amplitude, they're going to reinforce each other, and we're going to end up forming a bond. And if we bring two orbitals together, two wave functions that have opposite signs of the amplitude, they're going to destruct. And we're going to end up with basically what we call an antibond. So when we form a hydrogen atom, we bring two 1s orbitals that each have a positive amplitude. They reinforce, and what do we get? We get a hydrogen-hydrogen bond. The bonds overlap, and we end up with the electron density around the two nuclei. This blue represents the sphere. Remember from general chemistry, you may or may not remember, you may or may not have talked about this, but that wave function psi, if you square that, psi squared is the probability of finding the electron at any point in time. So why is an s orbital spherically shaped? The s orbital is spherically shaped because that's the volume of space where you're 95% likely to find the electron at any one time. Okay, and so that's where the shapes of orbitals come from, is that wave function squared. All right, so it's just basic waves. This is just another way of looking at forming bonds. And we're not going to get into the mathematics of what psi looks like or anything like that. So what happens if you bring two hydrogens together where psi has a different sign? In one case positive and in one case negative. Well, they don't reinforce each other and you don't form a bond. Instead, you form what's called a node. And from general chemistry, a node is a slice of space. It's a plane. It could be basically some type of space where the probability of finding the electron is 0. That's what a node is. Apparently there's hood problems this morning. But at least the hoods aren't beeping at us, which they are on the other side. So take it for what it's worth. So nodes are things where you don't find the electron. The probability of finding the electron is 0. That's the Chang definition. So when you bring together hydrogen of negative psi and hydrogen of positive psi, you end up forming a node, and so the electrons are not found between the two atoms like they would in a bond. And you get what's called an antibond, meaning that those two hydrogens don't form a chemical bond. Now, what happens is, in what's called molecular orbital theory, which is way beyond what I want to get into too much detail on. And I don't know if you talked about molecular orbital theory in Dr. Kwan's lecture. It'd be way back at the beginning of the semester. No, beginning of the year. But in molecular orbital theory, what you do is you construct for a molecule a series of what are called molecular orbitals. Back in general chemistry, you know that we have electronic configurations, right? 1s1, 1s2, 2s1, 2s2, 2p, whatever. You came up with those orbitals. Then you took the number of electrons and you filled up the orbitals. You gave an orbital 1 electron, and then when it got 2 electrons, it got filled, and you moved to the next one. We can do that with molecules by taking the atomic orbitals, the s's and the p's, or the s's and the hybrid orbitals, the sp1, sp, sp2, sp3s. We combine all those orbitals together to form what are called molecular orbitals. So in this case, hydrogen had one s orbital for one hydrogen, one s orbital for the other hydrogen, and so that gives me 2 atomic orbitals. Well, if I have 2 atomic orbitals, when I combine them together, I'm going to form 2 molecular orbitals. Okay? So hydrogen came with 1, the other hydrogen came with 1, that gives me 2 molecular orbitals. So I'm going to have a ground state orbital and an excited state orbital. Now, forget about those arrows being there for the moment. I got 2 atomic orbitals, I've now made 2 molecular orbitals. How many electrons go into these molecular orbitals? Well, hydrogen came with 1. The other hydrogen came with 1. That means 2. So when I look at this orbital picture where I've got my 2 molecular orbitals, I got 2 electrons to put in that. And so I put the first electron in, Then I put the second electron in to pair it up. If there was a third electron, it would go here. So I take my atomic orbitals, gives me the number of molecular orbitals. I construct an orbital diagram, sort of like S, 1s, 2s, etc. Then I take the total number of electrons and I place them into those orbitals. Everybody with me so far? I'll take that as a yes. Not that I can hear yes right now. So what does this mean? Well, look at what's going on. I have a ground state orbital and an excited state orbital. I now have the situation for spectroscopy. Right? Last week we saw that the energy difference between those energy levels gives you the energy that of a photon that would be required to promote an electron, to excite an electron. Well, in this case, I would have to hit this molecule with a photon of that energy in order to promote this electron to that electron, or to that electron from one orbital to the other. What would happen? If I hit this molecule with that energy and it was absorbed by the molecule and the electron moved up to the excited state, I would now put an electron into the anti-bonding orbital. Because these excited state and ground states are, here's my ground state bonding orbital, here's my excited state anti-bonding orbital. And we call these sigma and sigma star. A starred orbital is always an anti-bonding orbital. So what happens? If I apply enough energy to the hydrogen molecule, the electron moves up to the anti-bonding molecular orbital and the bond breaks. And the hydrogen atoms fly apart. Basically, that energy difference is bond dissociation energy. And so the idea here is that as long as you don't put electrons in the anti-bonding molecular orbitals, you get bonds. But the key thing is that it gives you now ground state, excited state energies, and you can figure out what the energy gap would be and what type of photon would be necessary, what energy of photon, what wavelength of photon, what frequency of photon would be necessary to have the molecule absorb. Okay, does that kind of make sense? All right, helium is a noble gas. We know that helium doesn't react, it doesn't form chemical bonds. Why don't two helium atoms form a chemical bond? Well, if you look at the two helium atoms, remember the electronic configuration of helium is 1s1, 1s2. So each helium has one 1s orbital. So the two helium atoms, if they were to combine, would make two molecular orbitals. We'd have a sigma orbital for the formation of the bond and a sigma anti-bonding orbital. Okay, so helium would have the same molecular orbitals as hydrogen. But when you bring two helium atoms together, what happens? Well, first helium atom has 2 electrons, the other helium atom has 2 electrons, so that you end up with now 4 electrons to place into those orbitals. So I put 1 electron here, pair it up, 1 electron there, and pair it up. And now what's happened? Now I have electrons in the anti-bonding orbitals, so that does a helium-helium bond form? No. And so helium won't form a chemical bond because the anti-bonding orbital is filled. So that's what we do. We take the number of atomic orbitals, combine them together to make the same number of molecular orbitals. Then we take the number of electrons and we fill up those molecular orbitals. And the energy gaps between the excited states and the ground states are going to tell us what photon of light, what color of light is going to be absorbed by the molecule. Except that what we said earlier was, or what I said earlier, was that double bonds play a role in ultraviolet and visible spectroscopy. So can you have bonding and anti-bonding orbitals for pi electrons? Yes. The top picture shows two p orbitals where the signs match up. The blues might be positive, the white negative. So that if you bring two p orbitals together with the same signs of the psi, they'll overlap and you'll form a pi bond like you do on top. Then, if you bring the opposite situation together, you now end up with two nodes. Because now you end up with an anti-bond formed between the p orbitals. Now remember, p orbital, because it has a top and the bottom lobe, there's a nodal plane that passes through the center of the p orbital. That's where you never find the electron. So the bottom one would be the anti-bonding p orbital, or the anti-bonding pi bond. So for ethylene then, CH2 or C2H4, two CH2s brought together with a double bond. For ethylene, there's two pi molecular orbitals. There's a bonding pi orbital, and there's an anti-bonding pi orbital. And if we just looked at those two orbitals, the p orbital has one electron, the other p orbital has one electron, so we'd have two electrons in the bonding p orbital. If I wanted to break the pi bond, what would I need to do? Apply just enough energy to promote an electron from the bonding orbital to the anti-bonding orbital, and the pi bond would break. The molecule would still stay together, right, because it's got a sigma bond, but the pi bond would break. So it turns out that this molecular orbital theory sets up the ground and excited states. And the energy differences between the ground states and the excited states occur in either the ultraviolet region or the visible region of the spectrum. But it's these pi bonding and anti-bonding orbitals that are the most important. But it's more complicated than that. Because in ethylene, where you've got a carbon-carbon double bond and 4 hydrogens, each carbon has 4 orbitals. So that's 8 orbitals from carbon, and then each hydrogen has a 1s orbital, so that's 4 more. Which means that the molecular orbital diagram for ethylene is not just two orbitals, it's a total of 12 orbitals, 12 molecular orbitals. Because 2 or 4 from each carbon and then 4 from all the hydrogens makes 12 total atomic orbitals that I'm combining together. So 12 orbitals don't fit on the diagram, or if they did top to bottom, they'd be really, really, really small. So this orbital down here is my lowest energy orbital going up, and then this whole column should actually be like right underneath this column. So the right-hand column should be underneath the left-hand column, so that if I'm looking at these 12 molecular orbitals in energy, I start with this one, and this would be number 1, this would be number 2, 3, 4, 5, and 6, and then this is 7, 8, 9, all the way to 12. So I have 12 molecular orbitals that could be constructed for the ethylene. And basically, I didn't really I let the computer construct those. So I didn't, they kind of look cool. You'll see like some of these pictures out in our artwork that we have out over by the Carabine lab, because they kind of look, some of these pictures kind of look cool just from an aesthetic picture. I have no idea what some of these things mean, except for a couple of the important ones. Like in the lowest, in the ground state, you got no antibonds. Everything's bonded. And then that orbital number 6 there, that's our pi bonding molecular orbital. And this orbital right here is your pi antibonding. your pi star or pi antibonding orbital. So the idea here is we got 12 orbitals. How many electrons did we have? Turns out we had 12 electrons in ethylene. So what that means then is that in each one of these first 6 orbitals, there would be 2 electrons each. In molecular orbital theory, there are 2 terms that are important. One is called the highest occupied molecular orbital, or the HOMO orbital, and the other one is the LUMO orbital, the lowest unoccupied molecular orbital. Okay, so as if we put these from top to bottom, the highest occupied molecular orbital, the orbital of highest energy that has electrons in it, is that one at the top. So that's the highest occupied molecular orbital. So that's the top of the ground states, basically. Then this orbital number 7 here doesn't have any electrons in it. So it's what's called the lowest unoccupied molecular orbital. And that's the beginning of the excited states. So that for ethylene then, your easiest transition, your lowest energy transition is going to be taking an electron from the HOMO orbital and putting it into the LUMO orbital. And then after that, the transition the energies get bigger and bigger, which means it takes a photon of more energy, which means it takes a lower frequency, or a higher frequency, lower wavelength. So in our molecules, this is what we'd have to do to figure out what frequency of light is absorbed. We'd have to figure out the energy gaps between all of these different orbitals. But if you studied molecular orbital theory in like an advanced class, the HOMO and the LUMO orbitals are the ones that usually we pay the most attention to. But they're not necessarily the only energy gaps that we get colors from. But this is where the ground state excited state comes from, is this idea. So other than this, it gets more complicated from here, and I'm not interested at this point in pursuing that. Other than this is the basics. So when we have a molecule that absorbs something in the visible region, okay, the visible region goes from about 400 nanometers, which is purple, or violet, up to the reds, which are in the 650s. Once you get below 350 or 400, you're in the ultraviolet region, and our eyes can't detect ultraviolet, really hardcore ultraviolet light. Black lights that we can kind of see with the sort of purplish color, they're in the 380, 420 region. Okay, but like the ultraviolet light that we use with UV light, it's at 254 nanometers, and so that's a much more energetic UV. That's like sun tanning UV. It's not burn your skin UV, that's ultraviolet C, which is much lower than that. That's what the ultraviolet they use for sterilizing stuff. Okay. So this is the visible region. And basically when we make a molecule that has a color to it, the color that we see is not the absorbed color. What we see is the transmitted or reflected color, which tends to be the complementary color of what's absorbed. So if you go back to your color wheel, which you can use to like choose complementary colors, then you have, for instance, the purples. The complementary colors of the violets tend to be the yellows and oranges, and vice versa. What's important is that if we have solutions of particular wavelengths and we know their absorption, that we can correlate that to what color they would appear. Okay, a blue solution would tend to absorb in this region, which can be in the 600 region, etc. So we can kind of use the complementary colors to figure out what we would see. It's not that easy, but that's a good approximation. So when people make colored materials, which, is an important economic business. Sherwin-Williams is, I think their motto is like cover the world in color or something like that. Everything that we have pretty much has a color to it, whether it's clothes, whether it's, paints, car paints, all of that has a color to it, and some of it has organic materials in it. And so if you want to make a molecule that has a particular color, you need to understand the molecular orbital theory to figure that out, but then you also need to figure out which wavelengths are reflected and which wavelengths are absorbed so that you can adjust your color properly. And there's people that do that. It's color science. I don't know anything about it. Other than it is a huge part of the chemical industry. And then getting those pigments or dyes to actually stick is another issue. Getting them to last is another issue. And so in a bottle of paint that you might put on the wall, there's a ton of stuff in there, each of which has a particular purpose to it. And car paints are even more tricky, because you got to stick them you got to put the clear coat on top of it to keep it from weathering. The particle size, because it's a pigment. Pigments are pigments. Pigments are solid materials. Dyes are water-soluble materials. And so like in a car pigment, the size of the pigment will change the color. There's some weird paints like the chroma key ones that look purple from one end, and then you turn your head and they turn like blue. And they were fashionable a while ago, maybe 10 years ago. But they're kind of iridescent color. All of that really is based on trying to come up with the right organic molecule that has the right reflection and right absorbance. So what we do then is this. If we look at this issue of conjugation, if you just took a double bond, it would absorb at 165 nanometers. That would be the breaking of the pi bond, going from pi to pi star. And 165 nanometers is in the really, really strong UV, like burn your skin to shreds UV. Okay, not tanning beds or anything like that. It's the really, really strong UV. Then when you make butadiene, which is the second molecule, you have now two double bonds in conjugation. Notice the wavelength gets longer, and now it's 217. Well, 217 is still very strong UV. When you get to three double bonds in conjugation, you're up to about 253 nanometers. And a benzene ring, an aromatic ring, also absorbs at like 254. When you take your TLC plate and you put it underneath the ultraviolet light, that ultraviolet light is emitting a 254 nanometer ultraviolet light that then strikes the plate, and there's a molecule there that fluoresces and turns the plate green. That's the type of wavelength that we're looking at. Black light wouldn't do that. So when we go to something that's really, really conjugated, like carotene, in carotene, you've got lots of double bonds in conjugation. Carotene is the yellow pigment that's in spinach. If you've done biology lab, I still think they do the TLC of spinach pigments. We did it in my lab. Carrots, the yellow pigment that's in carrots, is carotene. Look at, for all of those conjugation, your wavelength that it absorbs at is 452. What does it transmit? It transmits yellow. It transmits a yellow color, so the carotene looks yellow. So some practical, just a couple of them, that things that are food colorings have lots of conjugation in them to make them absorb visible light and make them transmit that visible light. So here's two red food dyes. Can't remember which one of these was like banned by the FDA back in the 70s, I think. There was a red color. They took red M&Ms off the market for a while because the food coloring was a tad bit toxic. And so the red food coloring number, whatever it was banned for obvious reasons. But notice what these are. Look at all the conjugation in the ring, all the double bonds separated by single bonds. You got aromatic rings. You got sulfate groups, S double bond O groups that contribute to the conjugation. We've got here an N double bond N. This is an example of what's called a diazo dye that you'll talk about how to make in lecture. So you want to make molecules that have color, you need lots of conjugation. From our structural standpoint, that means that if we have a molecule that does have a color, that means we have conjugation. We know that about its structure. Okay? And that's really all it tells us. If we get an ultraviolet or a visible absorption, we know we've got conjugation in the molecule. But from just a purely coloring standpoint, it's important to try and figure out how the conjugation relates to color. All right, so that's the basics, the real basics of UV-Vis. Later on in the semester, we're going to make molecules with some conjugation in the, I think it's the aldol condensation reaction. We're going to make one that's a really purple color. It's tetraphenyl cyclopentadienone. And it's got lots of conjugation, and it'll be a really dark, it'll almost look black, but it's actually a dark purple. And also we'll be dyeing fabric strips. We'll be making a diazo dye and using some different diazo dyes or different dyes to dye fabric strips, where it basically is a piece of cloth that has like cotton in one band and rayon and wool and silk and different nylons, so that you can kind of see the intermolecular forces that have to go on when you put a dye on a shirt, or when you put a dye on a piece of clothing. That goes back years, thousands of years. Royal purple was royal purple because only the royal people could afford that color of purple. But then there was a chemist named Perkin who actually made it by mistake. He was trying to make quinine to solve malaria, and he accidentally made this purple dye. And so that purple dye basically meant that everybody could wear like royal purple, and so it became like all the rage in Paris that year. But otherwise, the dyes came from like little insects and stuff that had to be crushed up, and the insects were only found in these certain islands in the Mediterranean. But dyeing fabrics and dyeing stuff has been around for years. There's a lot of even interesting chemistry that goes on in terms of trying to use intermolecular forces to stick the dye to the fabric. And even then, that's changed a lot as well through the years. It's easy to dye silk, wool. A lot harder to dye something like this, which is one of those like pseudo-athletic type, dry fit type shirts. When some of that stuff came out, it first came out in bicycle racing. I had the opportunity to talk to a guy at DuPont who made, I forget what he made. They made like one of the first like spandex lycra type stuff that people used in high performance cycling. There was a hollow fiber that somehow took the moisture from the inside through the hollow fiber to the outside and let it evaporate. I mean, we've gone a long ways since then, but sticking a dye to that became pretty difficult. And so there were, some of those materials, the dyes didn't work very well. Well, obviously now they work okay. So there's a lot of that goes into it, making the right color, etc. So color is a huge business of organic chemistry. A lot of industry goes into it.